So, welcome back everyone. We have already completed the syllabus of this chapter atom. In this class and in next class, in these two classes, we will discuss some numerical examples, numerical problems regarding this chapter. So, in last class, we have discussed about the X-ray and then Moseley's experiment. These things we have already discussed, and at the end of the chapter, we have also discussed a summary of the overall chapter. So, in this class, we will discuss some numerical problems. Okay, let me start with the first problem. Let me write down the problem first, then we will discuss. If the value of Rydberg constant of hydrogen is 109737 centimeter inverse, this is given. Then they ask to determine the longest and the shortest wavelength of the Balmer series. So, this is our question. Okay, they gave us the Rydberg constant. R is actually centimeter inverse. Now they asked to determine the longest and shortest wavelength of the Balmer series. So, what is the formula of wavelength for the Balmer series? We know 1 by lambda is equal to R 1 by 2 square minus 1 by n square. 2, why this is 2? Because they are asked to calculate for Balmer series. Okay, and n is actually variable here. It should be 3, 4, 5. In principle, it can goes up to the infinity. So, this is the case. Means like this is n equals to 1, n equals to 2, and 3, 4, 5. Every transition occurring from any higher excited levels to the level 2, n equals to 2, that will be considered as the line of a Balmer series, like this. So, these things we have already discussed, right? So, now we have to calculate the longest and shortest wavelength. Okay. So, first it is clear, when the transition occurring from n equals to 3 to n equals to 2, then the energy gap is minimum, the transition energy is minimum. As the transition energy is minimum, the corresponding frequency will also be the minimum, and we know wavelength and the frequency is inversely proportional. That means the wavelength will be also the maximum. So, for the longest wavelength, so longest wavelength would be when the transition occurred from 3 to n equals to 3 to n equals to 2. So, you can calculate, then 1 by lambda should be R into, R is Rydberg constant, that is already given to us. So, it should be just, we have to put here, now it is 1 by 4 minus 1 by 9, it is 36, 5 by 36. Okay. Now, this is unitless quantity. So, unit of lambda will be determined by the unit of R purely. R unit is 10,09737 into 5 by 36. This is, and it is centimeter inverse. So lambda should be 36 divided by 10,09737 into 5 centimeter. Okay, so this should be the lambda, the longest wavelength, but we have to do this calculation now. So now this is centimeter. Now we know that 1 centimeter equals to 10 to the power 8 Armstrong. Okay, so we can write it in terms of Armstrong unit as well. So if you do this calculation, numerical calculation, it will come around 6561 Armstrong. So this is actually the longest wavelength, and we know that the line of the Balmer series actually remains in the visible range, right? And it's evident from here. This is actually red region. Okay, so this is the longest wavelength, but we have to also calculate the shortest wavelength as well. Now here is the question: when the wavelength will be shortest, when the energy gap will be maximum, transition energy will be maximum, then the wavelength will be shortest. When the transition energy will be maximum, that's the question. So in principle it should be infinite to n equals to 2, and that is the case. Actually we have to consider the n equals to infinity as the level from where the transition is occurring. So for the shortest wavelength, we have to consider n equals to infinity to n equals to 2. Okay, but what does it mean? It does not mean that it's coming from infinity means very long, very far from the nucleus, or n equals to 2 level. That's not the case. We have already discussed these things. It's actually now clear, I guess, that n equals to infinity means is just the outside range of the nucleus, that where the field of nucleus is not acting, that is actually called the its nucleus. So let's say up to this part there is a field, then that outside that part, that is actually called as infinite. Okay, it's true for any electrical charge, any monopole plus q, any magnetic pole. For each and every cases, up to when the field is working, that is the range, that is the field of that charge. Outside that area, outside that region, where the attraction force or repulsion force, that means any impact of that charge or pole is not there, that is called the infinite. That distance is considered as the infinite. That means this distance infinite, this distance also infinite. So we can consider any distance as infinite outside this range. Okay, so that's why you have to consider here infinite. And when it's actually n equals to infinite, we have already discussed these things. At infinite level, actually that is actually outside the atom. It essentially means that where there is no effect of nucleus is there, there is no force, there is no impact of nucleus is there. That means it's actually came out from the atom. Okay, it's outside the atom, it's actually free electron essentially. So that n equals to infinity means the free electron. So we have to consider the free electron, which is coming to n equals to 2, and corresponding wavelength will be the shortest wavelength, as the required energy is maximum for the Balmer series. Okay, so let us calculate now. Okay, so what will be the what is the formula? 1 by lambda equals to r into 1 by 2 square minus 1 by infinite square, and it's straightforward. Infinite square is 0, so it's really r by 4, and r is 10 0. What is given? 9737 divided by 4. This is centimeter inverse, and similarly we can write it lambda equals to 4 into 10 to the power 8 divided by 10,09737 Armstrong. Just now we have to calculate this numerical value, and it's come around 3645 Armstrong. So you can see here this value is not lie in the visible range, it's actually in ultraviolet. Okay, so it's in ultraviolet, but generally visible Balmer series actually correspond to the lines which remains in the visible range, but here we are considering line regarding the transition which occurring from the n equals to infinity to n equals to 2. That's essentially does not mean the visible range, because when transition can occur from n equals to 7 to n equals to 2, that's give us the line in the violet range. So that's the lowest part of the visible range. We know that it started from the violet and goes up to the red, but here we are considering from the n equals to infinity, that's why it's coming out of the visible range zone. But still, as the electron is coming in n equals to 2 level, the final state, that's why it's also be considered as the line of a Balmer series. Okay, I think this part is clear. So this is the problem. Okay, next problem number 2. Okay, first let me write the problem. As a result of collision, with an electron of 20 electron volt energy, a hydrogen atom is excited. Excited to the higher energy state okay, and the electron is scattered with a reduced velocity. Okay, with a reduced velocity. Subsequently, a photon with a length, oh no, photon with wavelength 1216 angstrom is emitted from the hydrogen atom. Okay, determine the velocity of electron after collision. Okay, determine after collision. Okay, so what is given here? Okay, there is a hydrogen atom. Let's say this is a hydrogen atom, and one electron having energy 20 electron volt is coming and collide with the electron. This is our first rate. And what happens? The hydrogen atom get excited to higher energy state. It's excited. Okay, let's give us a star here. It's excited, and electron scattered with a smaller velocity. It's obviously because it gives some energy to the hydrogen atom, and using that energy, hydrogen atom got excited, and that's why the energy of the electron will be decreased. Okay, so now energy of the electron we have to calculate it, but the energy of the electron is decreased. After that, what happens? This hydrogen atom again goes into the ground state and release a photon h nu having wavelength this. So we have to calculate. So it's very easy. We have to just first understand what is the picture. There is a hydrogen atom there, and photon is coming, electron is coming, having the kinetic energy of 20 electron volt. It's collide with the hydrogen atom. It gives some energy to the hydrogen atom, and hydrogen atom got excited. This is the case, and the amount given to the hydrogen atom by the electron, that amount of energy will be decreased from the kinetic energy of that electron, and that will guide the reduced velocity of that electron after collision. That's okay. But now we have to calculate the amount of energy taken by the hydrogen atom from the electron during the collision. That's the case. And how will calculate that? Because using that energy, hydrogen atom got excited, and after getting excited it will again reduce to the ground state. It will again come back to the ground state, releasing a photon of that energy of which actually correspond the energy which was gained by the hydrogen atom from the electron during the collision. That's how you can calculate. So it's easily we can relate that h nu. So we can write it just like, let's say the energy of electron E before collision minus energy of electron after collision, it should be equals to h nu. That's the case. We have to just calculate this and we can evaluate the reduced velocity. Okay, so reduced velocity E prime, reduced energy after collision is actually E minus h nu. That means half m v square should be 20 electron volt minus h nu. From here we can calculate. So we have to now calculate this part. Okay, so what is the h nu? Here the h nu is hc by lambda. As we know, h is 6.626 into 10 to the power what, minus 34 joule second. C is 3 into 10 to the power 8 meter per second, and lambda is given as 1216. Armstrong means 10 to the power 8 centimeter. We are dealing with meters, so it's 10 to the power 10 minus 10 meter. Okay, so this is our results. We have to calculate what is the value. Okay, so now what will be the unit? First, meter will be cancelled out, second will be cancelled out, and it should be unit of joule. So it will be unit of joule. Just value we have to calculate. It will be 6.626 into 3 divided by 1216, and it will be 10 to the power minus 18 will goes there, so it will be 10 to the power minus 16, 10 to the power minus 16 joule, I guess. Okay, so now we have to calculate this. Let me calculate. So it's actually 6.626 into 3 divided by 1216. So value is 0.01634 into 10 to the power minus 16 joule. Okay, so this is the h nu. Now we can also shift the decimal point with changing the 10 to the power minus sign. So now it will be half mv square. We can write as 20 electron volt minus 0.01634 into 10 to the power minus 16 joule. Okay, now 1 electron volt is 1.16 into 10 to the power minus, sorry, it's actually 1.616. Okay, 6 into 10 to the power minus 19 joule. So it's here 20 is multiplied with this, so it will be 1.6 into 20 means 32. So 32 into 10 to the power minus 19 joule minus 0.01634 into 10 to the power minus 16 joule. Okay, we have to multiply these things, right? So now it will be we have to in same unit. So if you 10 to the 3, then we have to again multiply this 1 2 3, it will be 16.3. okay, we can write this. So it will be again 32 minus 16.34, it is 15.66 into 10 to the power minus 19 joule. It's half mv square. So now mv square will be, it will be multiplied by 2, so it is 31.22 into 10 to the power minus 19 joule. This is mv square, and m we know m is actually mass of electron. What is the mass of electron? 9.1 into 10 to the power minus 31 kg. So v square will be just we have to divide it. (31) joule per kg, and joule per kg, joule is actually energy, means Newton meter. Newton is actually kg meter second square. So it's the unit, and it kg meter square second to the power minus 2 divided by kg. So kg will cancel out, meter second to the power minus 2. Yes, excellent. So v will be 31.22 10 to the power it will be 12, I guess. Yes, 12 divided by 9.1 meter second inverse. Okay, so it's actually comes around 9.1, it's actually 3.44 into 10 to the power 12 meter per second. This is the velocity after collision. So it will be actually 10, it is actually 10 to the power, okay, let me calculate this, 10 to the power 12. Okay, so this is the value, and we have to take the root over of answer. Calculate this properly, because we have to take this root. It's actually comes around 3.44, so it's 1.8547, and root over 10 to the power 12, it's obviously 10 to the power 6, so it's 10 to the power 6 meter second inverse. So this is our reduced velocity after collision. So this problem is quite, it's also quite straightforward, but we have to just understand the physical picture first, then we can easily do this calculation. Rest of the part is just numerical calculation. So this is the final answer. So let me stop in this part here. In next part we will again discuss other numerical problems.